Now, this new chapter's name is Input Modeling, and at this chapter, we are going to start actually developing a model for the simulation that we are going to perform. So what is input modeling? We are going to explain. As you remember from the first chapter, I have told you that after problem definition phase and scheduling the project for a simulation project, the next step is model conceptualization and data collection. So at this step, while we collect data and we conceptualize a model in our minds for the system that we are studying, we are trying to develop input models for stochastic distributions. We have said that, for example, in a supermarket, the customers are arriving to a supermarket with random inter-arrival times, which follows a statistical distribution, okay? Or the duration for payments in the cashier points. They are following another probability distribution. The type of products that the customers are demanding, again, it has randomness. Or the time spent in the shelves by each customer, again, is a random traveling time. So all of these randomnesses should be modeled by a probability distribution. And here in the input modeling chapter, we are going to deal with that. So this chapter is going to continue for 4 steps. We have the data collection step. We are going to identify the distribution with data. We are going to estimate the parameter, and we are going to apply the goodness of fit test. So at this point, data collection means what? We are going to observe this real system for a while, and we are going to collect the data. And then in the second step, we are going to check the data, and we are going to identify a probability distribution for that data. And then after identifying the family of distributions, we need to select the parameter. For example, you say that the duration at payment is normally distributed. But in the third step, we need to define the parameter of that normal distribution. So what should be the location and the scale parameter? What should be the value of mu and sigma in that distribution? And after that, you are creating a hypothesis. So you are saying that the duration of the payment times are normally distributed with a mean of 30 seconds and a standard deviation of 3 seconds. So this is your hypothesis. Now, statistically, we need to check if this hypothesis can be true or not by again applying goodness of fit tests, just like we have applied for random numbers. However, this time we are going to apply a little twist in these algorithms, in this goodness of fit test, and we are going to be able to apply these tests to test if the input models can be correct or not. So this is the 4-step approach of input modeling. Now let's start. As I have said before, input models are the driving force for a simulation. So if you are, for example, developing a simulation model for a queuing system, the inter-arrival times of the customers, the time between the arrivals of consecutive customers to this queue, or their service times when they intend to take the service, are random times. So the customers do not arrive to a queue on a periodic arrival system. Actually, there are some queues like that, but these are not the queues that you may be able to observe in a supermarket or a hairdresser shop. Or there are service times, again, which are not constant but follow a random distribution. Now, another system is the inventory system, and in an inventory system, the inventory is depleted by the demand, and with the arrival of new product receipts, the inventory increases. The demand is a random phenomenon, random occurrence that causes inventory to deplete. And again, when we want to bring new products in our inventory system, if we want to receive new products, we need to release orders to our suppliers at an earlier time point, and the time between the release of an order and the arrival of a delivery is called the supplier lead time, and this is the delivery time of the supplier. So the lead time starts when you release an order to the supplier, and it ends when the products arrive. And this time is also a random time. Okay, for example, there are some reliable suppliers which have almost constant delivery time. For example, when you release an order, independent of the quantity that you order, they always deliver the goods in 2 days. But because of the traffic conditions, because of the weather conditions, because of other type of disruptions in the supply chain, this lead time may show a randomness. And because of that reason, even in the inventory systems, we have randomness caused by these lead times. If you want to simulate a financial market system, for example, if you have a stock portfolio, you can simulate the returns of the stocks in the future. So what type of return you are going to get. Or you can simulate the volatility values. Volatility is the magnitude of oscillation in the stock prices. If the oscillation is narrow, then you say volatility is narrow. But if the oscillation is large, if you observe huge price increases or huge price decreases, the volatility is large. Okay, so you see all of these, in all of these systems, when you want to develop a simulation model, the input models of these variables should be developed. So in stochastic simulation modeling, appropriate input models must be selected, and by input models we say the probability distributions. Statistical distributions for the inter-arrival times and the service times, demand, lead times, so on and so forth. The input modeling is an important step. If you choose faulty models of the inputs, which means you have said that it is normally distributed, however, when you check the data, it is not actually normally distributed. So if you choose a wrong model, a faulty model, statistically unfitting model, in that case, the outputs of the simulation or the results of the simulation will be faulty as well. And you are going to use these outputs and interpret them to come up with decisions, right? So we are running a simulation model to make a decision. So there is a problem and we need to solve that problem. And in the end of this solution, we are going to develop a policy, a solution policy, a solution methodology. Then your methodology, your solution will be a faulty solution as well, which will result with misleading recommendations. And obviously, you are not going to get the performance that you expect. Because of that reason, input modeling is important. However, there is this validation step. The validation step will help you to check if your models are correct or not. Because of that reason, I have told you that validation is the most important step in simulations. Now, my friends, there are 4 steps of input modeling, and these steps start with collecting data from the real system of interest. We have the real system. We need to watch that real system, observe it for an amount of time, and collect the observations related to the input variables. So data collection step requires substantial time and resource commitments, and the data to be collected depends on the problem that requires solution. So as I have said, problem definition is very important. So depending on the solution that you are looking for, depending on the problem that you want to solve, the input variables that you need to collect from the system may change. In some situations, it may not be possible to collect the data because the original system, the real system of interest, does not exist, or it exists, however, it may have some confidentiality, and because of this confidentiality, you may not be able to observe the system, or the hardware will not be available to observe such systems. So the underlying technology will not be sufficient to observe the system for a long time. In these cases, for input modeling, we do not collect data, but we use the expert opinion. For example, if we do not observe the stock prices data in a financial market, we can ask about the behavior of the stock prices to an expert. I mean, who has observed the market for years and years. So we can use the process knowledge as well to make accurate guesses as well. In these kind of situations, we usually end up with a triangular distribution in input modeling. Okay, so we talk about the worst case and the best case scenarios and the most likely cases, and then we use a triangular distribution as the input model. The second step is the identification of the probability distribution family to represent the input process. Identifying a probability distribution can only be practical or possible if you have sufficiently reliable data. You need to have sufficient number of observations, and it should also be reliable. The collection procedure should also be reliable. And we use visual descriptive statistics that you know from statistics course. Histograms, scatter plots, box plot diagrams, etc. Especially histograms and scatter plots are good beginning points to develop a probability distribution. So histograms, when you check the histogram of a data, the histogram can give you a fast idea about the probability distribution. However, there are some issues about that which I'm going to mention. So you should not just stick to the results that you see on the histograms directly because of the problems that I'm going to show you. We also need to think about the structural knowledge of the process, not just the descriptive statistics, but we also need to understand what we are trying to model. So for example, I can give you a data which seems to fit the normal distribution when you draw the histogram of it. Okay, when you check the histogram of this data, you can think that it is normally distributed. However, once I described for what type of process that this data belongs to, you may think about another distribution which looks like normal distribution. So you may think, for example, gamma distribution or beta distribution. Most of the distributions look like each other, so their histograms will look like each other. But this does not necessarily mean that you need to use the normal distribution at all times. Because of that reason, you also need to think about the structural knowledge of the process. So from what type of process this data comes from. Based on the structural knowledge, then you can limit the candidate probability models that you can identify for this data. Okay, so there are several candidate distributions. If, for example, you are going to model a continuous data, normal distribution, exponential distribution, gamma, Erlang, Weibull distributions are very well-known input distributions which can be used in input modeling. For discrete distributions, we can give the examples of binomial, Poisson, and geometric distributions. So aren't there any other distribution family other than these? Of course there are. There are maybe hundreds of distribution families like that, which you can use as an input model in a simulation software or a simulation model. However, it is impossible for us to cover all of them. If you want to really be a simulation expert, you definitely need to learn about these different input models from Wikipedia maybe, or from scientific articles. But in the simulation class, it is going to be impossible to give a list of everything. We are just going to focus on a few of them, just like in the list here. Now, the third step, after defining the distribution family, let's just say you have said that it seems like normal distribution. I have checked the data, and I have also knowledge about the process, and it should follow normal distribution. Then what you need to determine is the location and the scale parameter for that normal distribution. And how do we determine these parameters in each distribution? You know, exponential distribution has its rate parameter. Gamma, Erlang distributions have their shape and scale parameters. Weibull distribution has 3 parameters such as location, scale, and shape. Binomial distribution has size and the success probability. Poisson has the rate parameter, and geometric distribution has the success probability again. So how do we determine these parameters? From the data. So we use the data, and from the data, we choose a statistical, unbiased, and reliable estimate for these parameters. Then the fourth step, we need to evaluate the goodness of fit. So we apply the goodness of fit tests, and in this goodness of fit test, we test if our hypothesis is true. So let's just say in the previous 2 steps, you have identified the data comes from normal distribution and say that the location parameter is equal to the mean value of this data, and the variance of this normal distribution is equal to the sample variance. So this is your hypothesis. Now you need to check if this hypothesis is true or not. How can you do that? You can either use an informal way if you do not have enough time and enough knowledge. What you can do, you can use graphical methods such as QQ plots, okay? But you should be really an expert about that. I mean, when you look at the QQ plot, you need to understand with a single look at it. And this requires experience in statistics. So what you can do at this point is to use a formal way. What type of goodness of fit test we have learned so far? For random numbers, we have used chi-square and Kolmogorov-Smirnov tests. We can play around with these two tests, and we can also implement this test for testing if a variable really follows that distribution. We apply these tests not just for random numbers, not just for testing the uniformity. We can also test if other observations follow other distributions with this test. Now, let's just say that step 4, the test rejects the null hypothesis. So the null hypothesis is this. You say that our observations from the real system follow this statistical model. And the tests that you apply rejects the null hypothesis. So what you can do is this. You can go back to step 2 and choose another distribution family. Or, in the end, even if you continue to do that, you may not be able to identify a statistical model with a successful hypothesis test, unfortunately. In that case, you can use the empirical distribution and generate input variables or the random variables from the empirical distribution. Remember, I have told you how to generate random variables from empirical continuous distributions and empirical discrete distributions. You can directly use the empirical distribution model to generate random variables. However, my friends, this is still dangerous because, you know, most of the input variables in real systems, they follow a statistical model. So this normal distribution or exponential distribution and other distributions, they are not made up distributions. Okay, they are not just ordinary functions which are written by the scientists. Okay, they usually belong to a real life physical model. For example, most of the service time distributions follow normal distribution due to the central limit theorem. So there is a logical or physical meaning of these statistical distributions. So instead of using the statistical distributions, one can say that I do not need to perform a goodness of fit test for the input variables. Every time I am going to use the empirical distribution. So isn't it an approach? Yes, it is. However, the empirical distribution can be a wrong distribution based on the structural knowledge of the process. Okay, the structural knowledge may require a physically meaningful distribution such as normal or exponential. So always try to identify a statistical model that exists in statistics science. However, if you cannot identify a distribution family which can pass the formal goodness of fit test, in that case, you can freely use the empirical distribution. Now, if the test fails to reject the null hypothesis, then this means you can rely on the statement on the null hypothesis, which means you have an input model for that simulation. These procedures are going to take a long time because the data collection is going to take a very, very long time. And the other processes are trial and error methods for determining the statistical distributions. Again, it is going to take a long time. Today, with the knowledge on data mining approaches and machine learning techniques, this input modeling becomes a lot easier, but still, this time you need to learn the machine learning algorithms as an engineer. Machine learning is today the state-of-the-art knowledge on input modeling, actually. However, we are going to learn the basics in this class.